In this video, we are going to learn how to factor using complex conjugates. So in the last video, we went over how to divide complex numbers with complex conjugates, because we knew that when we multiplied them, we ended up just getting a squared plus b squared with no I. So that actually can be useful because sometimes we have an a squared plus b squared situation without the I, and that now we can use that to factor. So for x squared plus 81. These are both perfect squares. So I could look at x squared as a squared and 81 as my b squared. And then working backwards, I can see that, okay, the square root of x squared is x. And I'll get plus the square root of b squared is 9. But since this is a sum of squares rather than a difference, this will be 9i, and then the other factor would be x minus 9i. So they're still conjugates, but now they have this imaginary number since I know that two perfect squares come from complex numbers. So this looks very similar to difference of squares, but we just have an I on it instead. So over here, I would have 4x squared plus 9, but now the square root of 4x squared is 2x, and the square root of 9 is 3. But now we're going to use complex conjugates, so it'll be 2x plus 3i times 2x minus 3i. We often like to refer to this as the sum of squares. So up to this point, it was not factorable, not with the factoring techniques we knew and the numbers that we knew. But now that we know that complex numbers can exist, we can use them to help us factor a sum of two squares. So look at this next one. 2 and 32 are not perfect squares, but I see that both those numbers have a factor of 2 in common. So actually before I start, I can factor out the 2, giving me x squared plus 16, and now I can see those perfect squares where I have a squared, which is just x squared, and then b squared, which is just 16, and now I'll get 2 times x plus 4i, for the square root of x squared is x, square root of 16 is 4. The fact that we're adding these two perfect squares will make that a complex factor. And we'll get x minus 4i for its conjugate. Over here, we have 5x squared plus 20. Again, neither one of them are perfect squares, but they both have a factor of 5 in common. So I can factor out 5 before I start, give me 5 times x squared plus 4. There's my sum of two squares. I can use the complex conjugates, and this factors into 5 times x plus 2i, because the square root of x squared is x, the square root of 4 is 2. We're adding two perfect squares, so our factor will have I in it. And then we'll use its conjugate for the other factor, x minus 2i. Now sometimes it's not perfectly obvious, because 1/4 is a perfect square, but not of a whole number, but a fraction, because this can be thought of as x squared plus 1/2 squared makes up 4. So when I factor this, I'll get x plus 1/2 I and x minus 1/2 I, for that sum of two squares. Now you may also see this written as x plus I over 2, because they'll just multiply the two together. But either way of writing it is correct. Now lastly, we don't have a sum of two squares, but they're actually both negative, which means that if I were to factor out a negative, they'd both be positive, and that would set up my sum of two squares situation. So I'll factor out a negative, give me 9x squared plus 100, which both of these are perfect squares. So I'll get negative of square root of 9x squared is 3x, plus the square root of 100, which is 10. The fact that we're adding them makes that 3x plus 10i, and we'll use this complex conjugate as the other factor. There we go. Negative 3x plus 10i and 3x times 3x minus 10i. So you'll see the similarity to difference of squares is that instead of having just a plus b times a minus b, like you would see with x squared minus 4 would be x plus 2 times x minus 2. We just now include an I in that factorization instead. So very similar techniques. And that is how you factor using complex conjugates.